Yeah. All right, folks. By the way, a few announcements. So in our next lecture, I will be out of town. I will have a guest speaker. His name is Ed Chin. He's a member of my research group. Because I'm out of town, this class will not be videotaped, so don't expect it to be online. And really, I'd ask for you guys' courtesy in coming to Ed's talk. You know, I can put up with an empty room and people sneaking out, but it's not particularly nice to the guests to do that. Okay. I'll be in suburban Moscow. Don't ask if you guys need anything from out there. Let me know. I'll be spending more time on an airplane than actually in Moscow. In any event, let's see. That's coming up. Your homework is due next Wednesday, right? I can't have office hours Wednesday morning because I will be in suburban Moscow. Very cold. Not looking forward. Anyway, because of that, I'm thinking if we extend the deadline one day so that I can have office hours on Thursday, would anybody be strongly opposed to that? Okay, so that's what we'll probably do. But wait for an announcement from me. As of right now, the due date remains the same until you see something on Constructive. Okay? That way, we're all on the same page. That also means don't let me forget. I'll try and find a good time for substitute office hours. Your exam, it's time to slowly start thinking about the fact that it exists, right? It's in like how many weeks now? 2, I think, 3? 4? Emily thinks 4? 4, we'll go with 4. Your exam is whenever it is on the course calendar.
4 weeks.
4 weeks. So just begin thinking about that. That'll be right before the drop deadline for this course in case you're not sure. We'll make every effort to have it graded before that. Any questions about procedural stuff before we get started with class for the day? Cool. Yeah, in your next assignment, we'll be implementing all the stuff that we've talked about in the previous lecture today and in Ed's lecture. Next time, we'll be doing ray casting, ray tracing. I consider this to be one of the more fun assignments because it's a little, I keep saying this, it's a little easier than the one before it. And with just a few lines of code, you can render spheres and plates. and that's kind of nice. Yeah? And there's all kinds of fun extensions. Like for those of you who have asked about extra credit for this course or struggled on the first few assignments, I would recommend doing it for the ray tracing assignment because it's kind of modular and easy to extend in lots of different ways without breaking the pieces that you already made. Okay? Cool. All right, so today we're going to continue our discussion of ray casting and talk about rendering objects that are more complicated than spheres and planes, right? And then in our next couple lectures, we're going to talk about adding interesting materials, like things that are reflective and have PRDS and so on. So as a little bit of a recap, in our previous lecture, we defined what rendering is, which roughly is telling the computer to draw a picture. And there's many different variants, right? There's ray casting and ray tracing, which is sort of the first topic that we cover in rendering in this course. Right? That's the algorithm where the outer loop is over pixels in your scenes, and the inner loop is over all the objects, right? So the outer loop says for every pixel, I generate an array, and then the inner loop loops over all the objects and finds the closest one. Later on, we're going to talk about another algorithm called rasterization, which is roughly what your graphics card does. And rasterization, basically, in one sentence, just flips those two loops. Yeah? So the outer loop in rasterization is over every object in the scene that you paint one at a time. Right? And there are advantages and disadvantages to both, right? So we'll see that ray tracing is quite easy to implement. It's easy to include effects like shadows and reflection and so on. But rasterization can be very fast at the cost of things like occlusion becoming difficult, right? If I paint one object at a time, I got to figure out which one's on top, and that's a little bit trickier than if I just intersect with the ray and choose per pixel. Yeah. So, right. And then the other thing we covered is this idea of ray casting versus ray tracing. Again, I don't really care, but roughly ray casting is just you throw a ray out there and see the first thing it hits. Ray tracing is this extension of this idea that notices that once I have a piece of machinery for intersecting rays with objects in my scene, I can just keep using that to create all kinds of different effects, right? So for instance, if I want to have a reflective surface, I can reflect a ray off of the surface, send it back into the world, and find the next thing that intersects, right? So this one piece of code, which is find the first thing this ray intersects, is extremely powerful for capturing all kinds of effects. Okay? And then our last time we talked about how to set up a camera, our explicit representation of a ray, and then how to intersect with planes and spheres for the world's least interesting ray-traced images. Okay. Are there any questions so far? You can ray trace cool things like Sierpinski gaskets. In fact, we'll talk about that at the end of the lecture. Okay. So today we're going to talk about the sledgehammer of computer graphics, which is how to rasterize, or rather how to ray trace a triangle. And remember that once I can ray trace a triangle, ray tracing almost all the 3D objects that we have is not terribly difficult, right? Because we know that we can take most surfaces and cover them with lots of little triangles. And then once we do that, it's not so bad to render, right? You just loop over all the triangles one by one and render. Yeah. So today we'll talk about a single triangle, but what do you think is going to happen in practice? Is our algorithm going to be as simple as just moving over all the triangles on the scene and intersecting your array with each one? Probably not, right? I mean, the 3D models that you guys already worked with in your previous assignment had on the order of several thousand triangles, right? So that would mean for every single pixel you'd have to do several thousand ray triangle intersections to find the closest one. So in reality, in the next couple lectures, we're going to talk about structures to accelerate that process, right? To cull out a bunch of triangles rather than intersect with every single one. But if you're not concerned about efficiency, all you need is today's lecture and then you're good to go. So today we're going to talk about intersecting with triangles using something called barycentric coordinates. Barycentric coordinates is a topic that's close to my heart, as with most things in this class. But the basic idea is to take a point inside of a triangle and write it as a linear combination of the vertices of that triangle. Okay? And that'll be the barycentric coordinates of that point. More modern take on the barycentric coordinate problem that we won't study is, let's say that I have, some 2D human that I want to animate, right? One way I could do that would be to draw a little cage around that human. This is called cage-based animation for obvious reasons. Yeah? And I can start to drag the control points of this cage, right? And there's relatively few of them, right? They're just these coarse sets of points on this polygon. I suppose having a circular head is probably not very appealing. But, well, what I could do is take every point in the interior of the human and write it as a linear combination of the points on the cage, so that when I move the points on the cage, the human deforms with it, right? The difference between this picture that I'm drawing for you now and the one that we'll do in lecture today is that we're going to do barycentric coordinates in triangles, but barycentric coordinates in polygons that aren't just triangles is actually a modern topic of research and one that people think about quite a bit. Right? Because what we'll see is we're going to set up a linear system for our barycentric coordinates there, because we have 3 points and 3 coordinates, so that kind of works out. But here you've got a lot of points and 3 coordinates, so there's some degree of freedom to play. Okay. In any event, if you like that kind of stuff, you should Google for generalized barycentric coordinates. And actually, as course projects go, these ones are pretty easy to implement. You can get some cool, like bending and stretching style 2D animation stuff. Okay. So let's talk about the plane. So if I have a plane, in our last lecture, we talked about how we can specify a plane with a single point and a normal. But of course, there are many different ways to specify a plane sitting in 3D. And another totally reasonable one is to just give 3 points, A, B, and C, in the plane. Yeah, and of course, once you have 3 points, that completely defines the plane that goes through those 3 guys. Yeah, and so in particular, any point on your plane can be written as a linear combination of A, B, and C. So we're going to use the convention here, like alpha A plus beta B plus gamma C. And as long as alpha plus beta plus gamma equals 1, right? In other words, I'm kind of linearly combining these things in a way that looks like an average, right? Because you've got weights that sum up to 1. You stay inside of them. Does that make sense? So let's say that I give you a point in a plane, and I give you those 3 values, alpha, beta, and gamma. Can I check if the point is inside of the triangle spanned by A, B, and C? How would I do that? Yeah?
Alpha, beta, and gamma are all positive.
Exactly. Right? Because in that case, if alpha, beta, and gamma are all positive, it really is some weighted average of A, B, and C. Right? If one of them is negative, it means that I could extend to the outside of the triangle. Yeah. Right. So the coordinates alpha, beta, and gamma are roughly, well, they're exactly what we'll call barycentric coordinates for points on. And notice that alpha, beta, and gamma are totally intuitive, right? When alpha equals 1, it means that I'm on top of A. when beta equals 1, it means I'm on top of B. When gamma equals 1, I'm on top of C. Right? And I know that because all three of them sum up to 1. Does that make sense so far? Cool. All right. Of course, there are many different ways to write barycentric coordinates. Hopefully this first line here is pretty obvious. If alpha plus beta plus gamma equals 1, then we can write alpha equals 1 minus beta minus gamma. Yeah? So in particular, let's plug that in. Right? So if I have this expression for a point in the plane, I can substitute for alpha 1 minus the other two guys. Right? And then I can regroup my expression, and what I get is A plus beta times the vector B minus A plus gamma times the vector C minus A, which is probably the more familiar expression you guys have thought about for a plane. Right? All this is saying is that there's some base point A, right? And then there's a vector this way and a vector that way, and these sort of are forming coordinates along which I can okay? And notice that there's no restriction on beta and gamma anymore in this expression, because I'll just choose alpha to be 1 minus the other two guys. Yeah? And then they sum up to 1. Cool so far? It's going to be a real boring lecture if it's not. Might be boring anyway, but it's not a good one. Okay, right, so this is one way to specify points on a plane, and I think it's pretty straightforward and intuitive. Quick question, is this implicit or explicit? I would argue that this is sort of an explicit expression of point on the plane, right? Because in goes off beta and gamma, and out comes the point on the plane. We're not going to belabor this point a whole lot because I don't think it really matters. Right, so if I take alpha, beta, and gamma to be equal to one another, then that point is called the barycenter of the triangle. Right? It's equal to 1/3 A plus 1/3 B plus 1/3 C. And of course, if you guys remember your high school geometry class, the barycenter of a triangle has all kinds of nice properties, right? Like when I start drawing circles around the barycenter, and sort of, all these little Euclidean diagrams can show up in this form. So this is not going to be terribly relevant for our discussion today, but if you take a simulation class or you learn about finite elements, that stuff's going to matter quite a bit. But anyway, this is where this terminology comes from. Barycentric coordinates come from the fact that the barycenter is where all three of these guys are. Okay. Incidentally, there are two different centers, at least two different centers of the triangle. Like this is the one where you average. There's also the Voronoi center, which is where you average kind of moving orthogonally to the midpoints and the edges. They're not the same. Anyway. Okay, so right. So if I wanted to find a triangle rather than a plane, it's extremely simple to do so. Right? It's just the piece of the plane that's inside of the triangle, and like we already talked about, that's the case where all three coordinates, alpha, beta, and gamma, are greater than or equal to 0. Yeah? Or it turns out an equivalent thing to do is to just check that all three of them are between 0 and 1. So let's verify a few properties just for fun. So let's say that alpha equals 0, right? So in that case, we have P of 0, comma, beta, gamma, right? And this is equal to beta B plus gamma C. Yep. And of course, remember that now these two things have to sum to 1 because the third one's 0. Yep. So this is kind of like, let's see, equals beta B plus 1 minus beta C. And notice this is the expression of the line that goes through B and C. Right? When beta is 0, it's completely in C. When beta is 1, it's completely in B. So got something in between. And when alpha and beta equals 0, well, then necessarily gamma has to equal 1, right? And we get C. Yeah? So that's the kind of intuition you should have. It's like when alpha is equal to 0, right? In other words, the coordinate here has no effect, then I'm kind of as far away as possible from A. And when two of these guys are equal to 0, so like alpha and beta, well, what's the farthest point from those two guys? It's C. This is all pretty intuitive geometry. Okay? Right. So to summarize a little bit, our triangle, the plane expression is at the top. And if you want to be a barycentric coordinate, in other words, you want to stay in the plane, then you need the sum of all three guys to be 1. And if you want to be inside of the triangle, you additionally need 1 to be positive. Okay? Any questions so far? I think this is all kind of high school pre-calculus style stuff, but I think things that are easy to compute, but maybe we don't think about them carefully geometrically, and so it's worth double checking. So the next question we should ask is if I have a point inside of a triangle, how can I actually compute its barycentric coordinates, right? And there are many different ways to do it. I'll show you a geometric one really quick, and then we'll do the one that people actually do in practice. And it's easy to check what they're saying. Actually, the one that people don't do in practice is kind of fun to think about, and I encourage you guys to go on scrap paper and work it out, is if I have a point P inside of a triangle, and I want to know its barycentric coordinates, one way to do it is to say the barycentric coordinate with respect to A, which is alpha. What I'm going to do is define a triangle to be that point and the other two vertices. And I'm going to look at the ratio of the area of this triangle to the area of the entire triangle. And that'll be the first coordinate with respect to A. You can do the same thing with respect to B and C. We're not going to do it explicitly. You'll see that determinants are going to show up when we do our calculation. And so it's not all that surprising that this is hiding here. But it gives a nice intuition for what's going on. In particular, well, what happens when alpha equals 1, right? That's saying that the ratio between this shaded triangle and the whole triangle is they have the same area. So kind of necessarily it's pushing P all the way over here. Right? And similarly, when it's 0, it's saying that this triangle is degenerate, so it's along this line. Yeah, so it's kind of a nice geometric interpretation of what's going on. In reality, the coordinates are signed areas, meaning that if the triangle flipped over, like P is on the outside here, it would be minus the area. You can do that with the right-hand rule. Okay. But in reality, this is like a cute Euclidean construction, like what you might do with a compass and a straight edge. But computers are all about double precision floating point, and this is a nice picture, but it doesn't really tell you how to compute. Yeah. And so that's what we like to do next. Incidentally, there's a really fun iPhone game that you guys should all download. It's called Euclidean. Do you know this thing? If you're rusty on this kind of math. Where essentially they just they ask you to do things like find the perpendicular bisector and stuff. They actually managed to make it into a game. It's kind of fun. Anyway, okay. But in practice, let's say that I have the coordinates of A, B, C, and P, and I'd like to find the, like in 3D, and I'd like to find the barycentric coordinates of P. How could I do it? I don't speak English. Well, just generically speaking in this class, the answer to any question like this is linear algebra. Yeah? And indeed, this is no different, right? So let's say that I have a point P. I swear, this quantum guy is just like the worst. He writes on the board in such a way that you can't erase it. And they stay in this classroom way too late. Okay, right. So let's say that I have a point P. P's in 3D. And I'd like its barycentric coordinates. Well, what do I know then? I know that I'd like to be able to write P is equal to alpha times A plus beta times beta times B plus gamma times C, right? I suppose I should be careful with vector signs here. And I claim that this is nearly enough information to find alpha, beta, and gamma. You guys see why? I mean, it looks like I'm only giving you one piece of information. But why is that not really true? Yeah?
Linear combinations.
What was that?
You use linear combinations.
You use linear combinations. I'm not sure. So we're trying to go from A, B, C, and P to alpha, beta, and gamma. But the reality is that A, B, C, and P are actually vectors in 3D. Right? So this is actually 3 relationships. Do you see that? It's saying that Px equal to alpha Ax plus beta Bx plus gamma Cx Py equal to alpha Ay plus beta By plus gamma Cy, and so on. Right? So in fact, this is an invertible system of equations, even though it looks like I only wrote down one thing. Yeah, this is secretly a 3x3 matrix equation. Cool? Okay. Or a more slick way to write it would be if I took A, B, and C to be the columns of some matrix like that. And then I have the relationship remember how matrix vector problem works, everything like that, right? So this is alpha A plus beta B plus gamma C. Cool? So if I write like this, then it's pretty clear it's a linear system. Okay. And indeed, that's what we can do. So, but we can also do it in a slightly more slick fashion, which is, let's say that I wanted to remove some variables. And in particular, somebody gives me a piece of information, which is that P is in the ABC plane. Right? Well then, what do I know? Well, one thing I could do is say, let's draw our triangle again. There's A, there's B, there's C. All right, I'm going to define E1 to be B minus A. And I'm going to define E2 to be C minus A. Right? Well, what do I know? I know that I can write a slightly different expression, right, which is that A plus beta E1 plus gamma E2 equals P. Right? This is what we showed a couple slides ago. And now I've eliminated one of the variables, so life is a little, yeah. Okay. So if we do that, something's a little funky here, right? We have a linear system with 3 equations and 2 unknowns. And the reality is that I've secretly given you a piece of information that I haven't really used, right? That A, B, C, and P are all the same plane. So this only works in that particular case. And otherwise, the system isn't solved. Okay? And so if you wanted to solve this, one thing you could do would be to say, I'm going to take the dot product of both sides of this equation here with E1 and E2. Yes?
Just a quick question on the 3x3 linear system. Are we just going to assume that the inverse matrix always exists?
You should never assume that an inverse matrix always exists. Now, give me an example where it doesn't.
Well, in the case where like A and C would be relative to like some reference frame, C would just be a scaled up version of the A vector.
Yeah, so when A, B, and C are collinear, this matrix is not linear. Absolutely. Yeah. So one thing you can convince yourself is that when that happens is exactly when your problem is degenerate. In other words, like your triangle is collapsed. And so we're going to kind of just assume that doesn't happen today, but you're absolutely right. Anytime you write a piece of code that does this, you should like look at the determinant of your matrix or something and make sure that you can really solve this problem. Yeah, this is a problem that shows up in practice. We call these things sliver triangles, which are just long, thin triangles that just barely have non-zero error. It's a great question. Yeah. Okay, so far this is a little bit weird, right? Because unlike this version, which is 3x3, now we have 2 variables, right? We have 3 relationships, right? And so one kind of slick way to get rid of that is to say, I'm going to take the dot product with both sides with E1 and E2, right? So in other words, I'm going to use these bracket notation for dot product instead of the dot because I think it's easier to read. A dot E1 plus beta E1 plus gamma E1 E2. Like that. And so on for E2. This looks kind of complicated, but at least it's a 2x2 system. Do you see that? These are just scalars at the end of the day, right? So let's write this in a slightly different fashion. And glance at my notes to make sure I write it the same way that my notes have it. Right. So this is what we've done so far. So just take the dot product of that relationship, E1 and E2. And then somehow that makes sense, right? Because the interesting information in this plane, in this problem, is in the E1 E2 plane. Right? So somehow all I've done is just project into that space. Okay, so a different way of writing it is take a look. So what are the coefficients here? They're like E1.E1, E1.E2, E1.E2, E2.E2, right? So you can write a big matrix E1, 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 E2. Maybe for fun we write E2, E1, doesn't really matter. E2, comma, E2. Right? those are multiplied by beta and gamma equals what? 1 minus, and that's going to be E2 minus A. Okay. This expression looks a little crazy, but it's actually a nice intuition for what's going on, right? Because roughly, notice that this is on the right-hand side is really P comma E, P minus A, inner power is E1, and P minus A, inner power is E2. Right? So what have I done really? You guys see is I took P minus A, which is this vector, right? And I'm trying to kind of write it as a linear combination of this guy, which in this plane is like taking the dot product with E1, and this guy, which is in this plane taking the dot product with E2. That's all that's going on in that expression. Yep. And so, right, so here's our expression here, and if there's a God, these two things are yeah. Okay. Right, so at the end of the day, that's how we can write a point as a position inside of a triangle. And of course, remember that our goal in ray tracing is going to be to do what? Like, why are we going up to all this work here? Well, now what I'm going to do is take a ray and jam it into this triangle, right? And so remember our strategy for doing that? It's kind of like we have a parametrization of the triangle here. Sorry. And we have a parametrization of the ray, and now we have to figure out when those two things agree. Yeah? Okay. So that's our next step. So what are we going to do to be able to intersect a ray in a triangle? Well, on the one hand, we have P of t, right, which is equal to the origin plus t times the direction. Right, that's your point on your ray. And on the right-hand side, I have this point on my triangle, right? The base point A plus beta times B minus A plus gamma times C minus A. Right? And I solve this system for beta, gamma, and t. Yeah, and then there's an intersection if essentially alpha, beta, and gamma are all positive. Right? That's what this first condition is saying. And that t is bigger than whatever your minimum is. That makes sense? This is just one giant linear system of equations. As with most things in 6837. Okay, so right, if we want to write that out, it can be excruciatingly painful to do so. I've done so on the screen. I'm going to spare you guys the total boredom of my sitting here writing it on the board. But hopefully you can see what I've done. So here I took this bold expression here, and I just wrote it in terms of the x, y, and z coordinates. Yeah? And now these are a bunch of scalar relationships, right? The notation on the top is a little misleading because it's actually 3 relationships. Yeah? And so now I can write it by kind of isolating the beta, gamma, and t factors. I can write a p by 3 linear system, and life is good. Yes?
Just to understand, so the R naught and RD, that's
The ray.
okay.
Right? So R naught is the origin of the ray, and RD is the direction of the ray, and T is this unknown scalar, which is how far along the direction it needs to go. Yeah? And then similarly, we have two unknowns, beta and gamma, which are the position that's going to run into the ray. Okay? So you're kind of playing this game, right? So you have this ray going this way, you have alpha and beta, which like control where you are in the plane, and you're trying to choose the two things that they line up. Okay, and that's what this 3 by 3 system of equations is doing. Okay, so lucky for us, this is a 3 by 3 system, and it's an extremely easy thing to solve. We could do it by hand, but we're grown-ups here, so we don't do that. But one thing you might remember from linear algebra class is a particular formula called Cramers Rule. You guys remember this one? So Cramers Rule is a way to compute the inverse of a matrix explicitly in terms of the determinants and its minors. But even if you don't, here it is. So here the vertical bar is determinant. And this is just one giant expression for the inverse of your matrix. This doesn't matter a whole lot. Please don't write it down. But it does tell you a little bit about what's going on here. Right? So in particular, the thing in the denominator of all three of these is the determinant of the whole matrix. Right? So going back to the question we had before, when does this thing fail? Well, it fails when this determinant is equal to 0. Yeah? And if we look, there are a couple different ways that could happen. Right? One would be that these two things are parallel to one another. Unless think intuitively, what does that mean? That means that A minus B and A minus C are parallel. So in other words, like remember that those are those two vectors along the sides of my triangle that in fact are parallel lines, right? It makes sense because then you don't really have a triangle. And then the other one is when R is parallel to either the sides of the triangle or some linear combination thereof. And why does that make sense? So that's kind of saying I have a triangle down here, and then I have a ray up there moving parallel to it that never intersects. So it's all pretty intuitive stuff. The numerators, when do those go to 0? I have to think about it. But it doesn't really matter. Okay, so at the end of the day, if I want to implement code in my ray tracer to render a triangle, what do? It's pretty straightforward, right? I have a ray whose origin and direction are prescribed, right? That's RO and RD here. I have a plane where I have points A, B, and C. And just basically by typing in these three formulas, I get the parameters of the intersection between those two things, and I'm done. Right? This is true for a lot of ray tracing. It's just like you do a lot of algebra on your scrap paper, and then you just type it in. Like, algorithmically, it's not terribly complicated, and mathematically, it's kind of enough. Yeah. Are there any questions about this construction here? Cool. And incidentally, you could use this for ray plane intersection as well. It's a little too complicated. Yeah? And so, why do we like barycentric intersection? There's a lot of reasons. One is that it's easy to distinguish inside of the triangle from outside. Right, in the previous lecture, we intersected rays with planes, and essentially this is doing the same thing. It just gives you an additional piece of information, which are these three numbers, which are positive when you're on the inside. But there's actually a second reason that we like barycentric coordinates, which is something that turns out to be incredibly important in graphics, and one that we'll return to several times in the coming weeks. So there's a lot of information on a triangle mesh that we tend to store per vertex, right? All kinds of things like texture coordinates, sometimes the normal vector, sometimes color, whatever. But here's the reality: is if I get all up in my surface's business, there will be more than one. The pixels are going to go into the middle of the triangle that I have to render. Right? So if I have color per vertex of a triangle mesh, and I want to render this thing and I hit the middle of the triangle, what am I gonna do? Well, in fact, what I have to do is interpolate. Right? I need to take these three values on the three vertices of the triangle and somehow guess what the value should be in the interior. Yeah. And one totally reasonable way to do that is to take a weighted average of the values of the vertices using the barycentric coordinates, right? Because they have this nice property that the closer I am to one of those vertices, the bigger the weight is of that vertex, and that the three things always sum to 1, right? So there's some kind of weighted average. Yeah? And so I've shown you the results of barycentric coordinate style interpolation here. So here I have three vertices where I'm additionally saying that there's an RGB here, which is 0, 1, 0, 0, 0, 1, 1, 0, 0 at the three vertices. Then I'm barycentrically interpolating the red, green, blue values to the inside. And what I get is this nice color render. By the way, notice in the middle it's kind of grayish. Why does that make sense? What is the RGB value here? It's 1/3, 1/3, 1/3, right? So notice this actually also shows us a little bit of a drawback of this the interpolation procedure, right? Because on the corners we've chosen the most saturated colors possible, and in the center we got something extremely unsaturated, right? Something kind of dark. Yes?
So why are colors stored per vertex and not per faces?
Sometimes they are.
Oh, it's just
No, so the reality is we actually usually don't store color per vertex or per face, although we'll see that we store material properties like BRDF per vertex per face. So one reason you don't store information per face often is that you'll have a discontinuity along an edge. So the reality is that your eye is extremely sensitive to sharp changes, right? And so one good way to make sharp change is to store one number per triangle and have it just change along the edge. So a reasonable way around that is to store one number per vertex. Turns out your eye is also reasonably sensitive to C1 discontinuity. In other words, like changes in slope. And making something C2 smooth turns out to be quite annoying. So you can do it by additionally storing a number in the center of every edge. That's a kind of advanced thing. But the reality is that oftentimes, basically, there's a lot of information that we like at as fine a resolution as possible, we don't want to store the mesh to be super, super dense, right? Like if I had a 3D model of my hand and I want to display this texture of my skin, right? I wouldn't want a single triangle every single time my skin folds up and down, right? That would be a lot. So instead, typically what I'll do is I'll have a coarse 3D model of the body, and then maybe not a color per vertex, but maybe actually position in some photograph of a piece of skin. This is called a texture coordinate. And so if I have a texture coordinate at these 3 vertices, then one thing I can do, so let's say that I have, God, I hate this guy. Okay. I can't erase anything in here. So let's say that I have a 3D model of a hand. So here he is. It's a hand. And somewhere on that hand is a triangle, right? Then in addition, what I'll do is I'll have some 2-dimensional image like this, which is a very detailed photograph of is the hand, right? And every one of these vertices of this triangle will have a position in the photograph, right? And typically I can store the photograph at much higher resolution than I store the triangle mesh. And what I'll do is if I want to render a point in the interior, well, I have these 3 points. So I compute his barycentric coordinates. Then I use those barycentric coordinates to find this point inside of this triangle, and that's the pixel color that I read. Right? And this is a reasonable way to get a much higher resolution looking texture on a low resolution 3D model, which is a pretty typical thing to do. Like for instance, in this algorithm here, you can see the expense increases with the number of triangles you have. Right? So you might want to keep your number of triangles low, but then do some pretty complicated texture computation behind the scenes. Cool? How's that for a long-winded answer? Okay. That's called a texture lookup, by the way. Okay, so right, so this is the basic idea of barycentric interpolation is that once I have the barycentric coordinate of the point, now if I have some value per vertex, I can just use those same alpha, beta, gamma values to sample it into. Yeah, and that's kind of a sanity check. One thing you can notice is that when you're at the point, you really do get the value there. All right, any other questions? This allows you to do nice things. Like probably this ugly vase in the background of this scene is not actually having triangles at the resolution of these little bumps. My bet is that it's a very coarse triangulated mesh, and then what's sitting behind it is the texture. And by the way, fun fact, and then I'll get off of my soapbox here. Do I have to store color in this texture image? No, I can store whatever the heck I want interpolated along the triangle. This is a realization people had over 20 years ago, that they can kind of hack their shaders to do all kinds of crazy stuff. Right? So for instance, I can have a very high frequency changing material along my surface, right? And essentially use the texture lookup to look up the parameters of my material, like have the shininess change as a function of where I am. And then do the texture lookup, read it back to where I am, and then do some computation with it afterward during the rendering procedure. Yeah. And so there's all kinds of things. So for example, the reason why this came to mind is my bet is what's going on here is they use something called a normal map, where at every point in this texture you store a normal vector to the surface. That way you kind of have this micro normal going on the surface, even though it's a triangle, it's flat, which is kind of a cool way to get additional detail. Okay. Cool. So that concludes our discussion of intersecting triangles and rays. And I think we've really belabored it at this point. But that's the basics of how this ray tracing stuff works. I come up with a new primitive that I'm interested in, and now my main job is just to figure out how to hit a ray into it. Okay? Great. So as a quick digression, we already talked about this a little bit, so we're not going to go too crazy about it, and then we'll go on to a new topic. One thing that's worth noting is that ray casting is a great example of object-oriented design. In particular, notice we now have 3 different primitives, right? We have spheres, planes, and triangles. And if I want to ray trace, what do I need? Do I need to know what kind of object it is? No, I just need to know that it's a thing I can hit a ray into and that it'll give me back a normal vector, right? And so that's a great excuse to do object-oriented programming. Right? So, of course, now that you guys are going to learn how to do this in C++ during your current assignment in physical simulation, you'll also do it in your ray tracing assignment as well. Okay? So in particular, typically what you'll have in a ray tracer is some generic class like Object3D, which has inside of it this Boolean function intercept, which takes array, some t-min, in case my eyeball is offset a little bit, and a hit record that it can return information about the intersection. And then it just returns like yes or no, did it run into it, and if it does, modify this thing, right? And this is what you code in your assignment. And then in particular, you can have subclasses of this guy, like plane, sphere, triangle mesh, maybe a group which itself contains other things. And from the perspective of the ray trace, it really doesn't matter which one it is, right? And that's why these things are pretty easy to implement. You can similarly abstract away the camera, right? You could just have some class that takes a pixel position and returns a ray. And that's perfectly fine. So in assignment 4, you'll be actually implementing this stuff, and you'll make a raycaster, and I believe do some simple ray tracing. I forget if that's required or not. If it isn't, it should be. Think about that.
Have reflections on refraction.
Oh, that's what it is. Yeah, you do have to make reflective stuff, but reflective is pretty easy. And refractive material is easy too, but it turns out idealized refractive stuff just never looks very good in a ray tracer. You really need like impurity on a piece of glass before that's convincing. So you can try that, but it's not terribly exciting. And we'll give you some classes for arrays and a hit record and a material, and your job is to intersect and do that kind of stuff. Any questions about that before we move on to more advanced things? Cool. And there's like millions and millions and millions of textbooks out there on this stuff. My favorite is actually this middle one. This was my very first computer science textbook, which I found in a bargain basement in the 90s. And it's still around today, many editions later. And just goes, it's this tiny little book that just goes through how to implement a ray tracer and add cool features to it. Okay. So as our next task, we're going to talk about constructive solid geometry, which is used for modeling all kinds of cool environments, both in ray tracing and in rasterization, although it will be much easier to ray trace than to rasterize. Okay? I think one of the earliest rasterized versions of CSG was using these Max Payne games. I think what survived was CSG. I don't think that Max Payne is a thing people still play, but I could be wrong. Right, so the idea of constructive solid geometry is to borrow some ideas from Boolean algebra and make them work for a shape. So you guys remember Boolean algebra from your intro computer science kind of stuff? Yeah, this is like if I have two binary variables and I take their AND or their XOR and so on. And for every one of those operations, there exists kind of an analogous operation on a shape. Right? So for instance here, I have two shapes, a cube, which is object A, and a sphere, which is object B. In a sense, if I render them both together, that's their union. I would say that's the kind of boring case here. But I could also do something like subtract the sphere from the cube, in which case I get a cube with a little bit out of it. Or I could take their intersection, which is just that, the thing that I did. Yeah? And so these are what we call constructive solid geometry. The idea that I can construct a pretty complicated shape, like this thing on the right, by intersecting and unioning and differencing simpler primitives. And this is by far, I think, kind of the basic technique in computer-aided design beyond splines. Right? So we already talked about like tensor product patches and quadratic patches, all that kind of stuff many lectures ago. Essentially, the two big things that are implemented in CAD system are those, and then ways to take those things and intersect them in collaborative ways. Now, first of all, let's say that I actually, like, the only thing I know how to do is render a triangle mesh. And I want to render this guy on the right-hand side. Is that easy or hard? Like, maybe I have a triangle mesh of the sphere and a triangle mesh of the cube. That's hard, right? If I give you two triangle meshes and I ask for a triangle mesh of their intersection, that is a tough computational geometry problem. Yeah? And it is not obvious how to do it. But what we're going to see in ray tracing is that it's unnecessary, and we can actually sneak our way around it by just keeping these two primitives around and doing some clever computation. Okay? And CSG can do some really cool stuff with some pretty simple shapes. In fact, this is a good one to try on your assignment for extra credit after you save your original version. Yeah? So for instance, if I want to make this kid's toy looking cute shape thing on the top, well, how can I actually model this? Well, I could take a sphere and intersect it with a cube, right? That cuts off these circular faces on the top and on the sides, right? That's this shape here. And now I could subtract out the union of three cylinders, right? Which gives this guy here. And then what I'm left with is a pretty complicated shape. Okay, so you can see that one of the nice things about CSG is that once I just have machinery for like doing maybe planes and spheres, I actually can get some pretty interesting shapes. And by the way, I wouldn't even bother modeling a cube. I would probably just do planes or half planes. And so there are all kinds of nice examples. Here's another one. This cute model, the left-hand side of like a, I don't know, a votive, is that what you would call that? Like a candle holder with little star and moon shapes cut out. And we're going to see is pretty straightforward to model. In fact, here you can see like a cutaway of some of the CSG that we're going to. But as a high-level story, it makes some sense. I think this is a pretty straightforward thing to want to do, even if we don't know how to do it out in the neighborhood. Okay. Right, so the basic CSG operations we'll talk about today are shown on the screen. So we're given two overlapping shapes A and B. We'll look at their union, which is the intersection of these, which is the space covered by both of these guys. The intersection, which is the space that's covered by both A and B, and then the subtraction, which is like the set of points that are covered by A but not B. Yeah. And these are the things we want to render. It's easy to neglect the union when you talk about CSG and just sort of say, like, well, I could just render both of these shapes. Like, from the viewer's perspective, maybe it's the same. When would that run into trouble? Any ideas? Yeah? Exactly. Transparent machinery, or material will get you in trouble. Because if I build if I take two glass balls and I glue them together, I don't want the light to refract in the interior of the shape. I only want it to happen on the outer surface. That's absolutely right. Okay. Right. So, how are we going to implement CSG? Well, unfortunately, initially it seems kind of complicated, right? We need to deal with all kinds of different cases, like points that are on A and outside of B, points that are on B inside of A, and so on, right? But the trick in ray tracing, ray casting, is that I never actually need the surface of the shape, right? All I have to do is check if a ray intersects the surface of the shape. You see that those are slightly different things? That I don't need a triangle mesh of this crazy cube with a sphere bitten out of it. I just need to know if a ray ran into it. So how could I do that? Well, one thing I could do would be to intersect my ray into both the sphere and the cube, and then kind of notice, does that intersection happen inside or outside of one or the other, and keep track of it that way. Yeah, so let's formalize that a little bit. Right, so what we're going to do in our CSG style ray tracer is keep track of a slightly different piece of information, which is not just when the ray enters an object, but also when it exits. Okay, and we're going to be able to process a bunch of rays independently to do our CSG, rather than kind of construct the shape and then intersect your ray with it. Yep. Right. So one thing that you could do would be to intersect. For example, if I wanted to compute the intersection of A and B, one thing I could do would be to compute the two intersections of my ray, and then kind of just do a bunch of logic to figure out is this point inside of the other model or not. That gets complicated really fast, right? If the more shapes I intersect, the more things I have to do inside-outside computation for, and so on. And so instead, that's really not the typical strategy. Instead, what we do is we keep track of intervals where a ray enters and exits an object. Yeah. So for instance, let's say that I want to render the intersection of A and B. Right. So what I could do is intersect my ray with shape A, right, and say for t values between t0 and t1, I'm inside of the shape. Yeah. Do the same thing with shape B, right? Now I have these two intervals, the red one and the blue one, and I just take their intersection, but intersecting one-dimensional intervals is pretty easy, okay? And that's going to give me the t-index of the first thing that I run into, okay? And that's the trick, is you keep track of an entry and an exit for every shape, okay? So in other words, what we've done is we reduced our problem from some crazy intersection of two spheres to a one-dimensional thing. Yeah, it's pretty cool. Something that's worth noting is that CSG is easy for ray casting, but it's really hard to get an explicit thing of the surface. One issue that is kind of a side effect of that is that oftentimes right near kind of corners of things you can run into some numerical trouble with CSG stuff. And so when you implement this, for example, a pretty common thing to do would be to add a couple of digits of precision to what's your normal double precision floating point or something. Just to avoid all these crazy kind of issues. So let's do an example. So let's say that I have the origin plus t times the direction, Yeah, and I figure out that I'm in shape A, which is this circle, for t values between 1 and 3, and I'm inside of shape B for 2 and 6. And I want to intersect, I want to render the intersection of these two shapes, or the difference in union and so on. And I think this is not so hard. Yep. So what is the interval of A minus B? So remember, this looks like 1, 2, 3, 6, right? So what was that? Yeah, so this would be 1 and 2, right? This is this interval here, which is where you're inside of A but not inside of B. Yeah? You could have got it by just looking at these two intervals and noticing that if you take the range 1 to 3 and remove this guy, what's left is 1 to 2. Yeah? Similarly, what's the union? 1 to 6, right? It's all the possible t values that are covered by either one. And finally, what's the intersection? 2 to 3. But notice that I could have not given you this diagram on the left and just given you this information here, and you could have still computed those intervals. Right? And that's the key thing about ray tracing. Does it tell you the actual shape of the intersection? No. Right? It just gives you some means of intersecting rays. It's kind of cool. I really like this trick. Hopefully we got it right. Yes, good. Okay. Right, so again, I guess we've already mentioned this, but the floating point is a little bit of an issue, especially, like, does this thing enter and exit the sphere at the same point? What does that mean? That's a good a way to have a bug. So it's just something to think about a little bit when you intersect. So typically in your code, and this includes in your assignment, you'll have some magic epsilon number floating around, which is like the fudge factor. And it essentially says, like, if I nearly intersect within some epsilon value, I'm going to count it as an intersection or something like that. This is just a way to essentially say that I don't care so much about a precision rendering. I would prefer just not to get noise in the boundary of an object. And this was quite important. So in fact, when I used to teach graphics at Stanford, they did it in the other order. So we would cover rasterization and then ray tracing. I think this order actually makes a little more sense because this is easier. And the assignment that I gave, and I got total mutiny on the part of my students, was just render 2 triangles adjacent to one another in a way where the edge between them has no holes and where the 2 triangles never write on the same pixel. And if you think about it, this is extremely difficult to do, right? Because you know, if my triangles are kind of transverse to the grid of pixels on my screen, I can have to decide what inside and outside is in a reasonable fashion that is consistent on the 2 sides of the triangle, or else I end up with a hole. If you read the documentation for your GPU, you'll notice that they have extremely careful ways that they talk about how they rasterize triangles for exactly this reason. Because it would be pretty awful if your video game had a bunch of seams on all of the intersections of the triangles. Okay. So anyway, this is an easy thing to get wrong, and this is one of the big reasons why we have this epsilon value. But if you get it right, you can do nice things like these ugly marble Stanford plots. So any questions about CSG? I think the basic idea is pretty simple, and it makes really nice shapes. Right? Basically what you do is, rather than just keeping track of the closest intersection, you keep track of the interval during which your ray is inside of a shape. Right? And that way you can union, intersection, subtraction, and so on, just by doing 1D interval math instead of higher dimensional stuff. Cool. Incidentally, one kind of annoyance there is remembering which normal to give back when you render. That's not hard. You just kind of have to attach normals to the beginning and end of every interval. But it's an easy thing to screw up. Okay. So as one final topic today, we're going to talk about transformations in raycasting. We notice one thing that we do a lot in 837 is we kind of introduce a new topic, and then we go down the laundry list of all the things we've already covered in this class and show how they connect to it. And that's what we're going to do next. So just like we talked about, applying matrices and things to shapes. So like I take a sphere, I apply a matrix to it, and that maybe shifts it, translates it, shears it, whatever. I can do the same thing in raycasting. It's a little annoying, right? We haven't really actually figured out a reason why. And that's going to lead to a technique called instancing. So in particular, let's say that I would like to render this like weird stick figure satanic ritual thing going on in this image here. Right? So notice that there's a single 3D model that's getting repeated many times in a circle. Right? And essentially the only difference between these guys is color and vision motion. Or similarly here, I have a chessboard. For some reason, this glass dragon's chilling in front of it. And once again, I have a lot of repeated elements, right? Like the chess pieces and the squares and so on. And just like we talked about when we talked about scene graphs, Remember, there's really no reason to repeat these things storage-wise, but we still have to figure out how to render them. Yeah? Right, so if I have a lot of repeated objects, what would I not want to do? What I probably wouldn't want to do is take this one, I gotta replace this image. It's like one, for some reason it really creeps me out. But anyway, this one stick figure with a top hat, and just copy them 1,000 times in my code. Right? That wouldn't be like a very efficient way to use space. So instead, I'd like to be able to intersect array with a translated shape. Does that difference make sense? Okay. And so another way of putting it is that I'd like to store once and use often. And that way, if I want more rings of stick figure guys worshipping the black pole, I could do that, and it won't cause too much problem with my ray tracing. Okay? And so the basic idea of instancing, which is going to fit really, really nice with object-oriented programming, is I'm going to have a new class, which has sitting inside of it an object, and outside of the object it stores a transformation that it applies to it. Right? The great thing is that does the class that applies the transformation need to know much about that object? No. Right? That's what's so cool about ray tracing. Yeah? In particular, this is going to be our basic setup, is that every time I have a new instance, a new stick figure dude with a top hat on, it's going to store a new transformation matrix with it. Yeah? And I can stretch, rotate, whatever. So of course, what do I have to do now? I have to intersect array with an object to which I have applied a transformation. That makes sense? So here's the nice thing. What happens if I take array and I apply a linear transformation to it? Can it turn into like a sine curve? No, right? When I apply a linear transformation to a straight line, unsurprisingly, it's a linear transformation and it stays a straight line. Right? And implicitly, that's what we're taking advantage of. Right? So what we're going to do is say, okay, I have two options, right? I can take a sphere and I can stretch it out and make it into an ellipse, or I could leave my sphere alone and apply the reverse of that transformation to my ray, and that way I can just keep my old ray sphere intersection code and not have to worry about it. That's kind of sneaky. I would encourage you guys to add this thing to your assignment because it can make for interesting scenes, and it's a good way to test to make sure that you really understand the geometry going on in this class, because it's easy to get the matrices wrong here, as I typically do. And so at the end of the day, oftentimes you'll see files that look like what I'm showing you on the screen for storing a scene geometrically, where maybe you have a transform, like translation and scale, and then inside of it you have a sphere. Or maybe inside of this thing you actually have another transform, and then a sphere, or whatever. How many of you guys have played with VRML files? Wow, interesting. So about 15 years ago, we were convinced that the future of the internet was 3D. You can see how well that played out. And so they were going to replace HTML files with VRML, which is virtual reality modeling language, which was a description of a 3D scene that you could load in your browser. And I remember old versions of Internet Explorer, you could load this thing in just like an HTML page, and it would pop like a 3D scene. And that way you could like walk around your web page, I guess was the concept. I'd say this technology was a little before its time. Like, rendering wasn't good enough to make it really valuable to do that. But in any event, if you look inside of a VRML file, you'll see that this is basically what it looks like. It's just a bunch of nested transformations. The kind of funny thing it has is, in addition to that, it also has a machinery for adding hyperlinks, so you can like, touch something in your 3D scene and go to the web page. It was an interesting kind of historical artifact. I'd be curious. Actually, I don't know if modern web browsers can still open these or not. Probably not. Right. So anyway, right. So there's sort of two different ways to go about transforming something. Right. So for example, I can transform a sphere to a translated sphere. I think that's not a big deal. But even intersecting an array with an ellipse rather than a sphere, it's like not totally obvious. Right? There's like a lot of algebra you would have to do. It's not hard algebra, but it's kind of a headache. Right? So instead, just like remember when we transformed normals, we talked about how there's a particular way to do it. We do a similar thing with a ray, right? Which is to say, this ray is a straight line in world space, in the space where the ellipse looks like an ellipse. But if I apply the transformation which takes this ellipse to just a sphere centered at the origin, that straight line stays a straight line because I'm still just doing something linear to space, right? So in particular, if I say that a point in object space translates to a point in world space through a matrix M, right, then of course the inverse of M is the other way around. Well, what do I need to do to my array? Well, I need to do two things, right? I need to mess with the origin of my array, and I need to mess with the direction of my array. How do I do that? What do I do to the origin of my array? If I have, the origin is in world space, right? That's where I'm doing my rendering, right? And what I'm saying is that the shape that I'm interested in rendering is m times, you know, a shape that's sitting in its own object space. And how do I get the coordinates of the array in the object space? Well, m goes from object to world, I have array in world. What do I do to its origin? M inverse, yeah, absolutely. Because M inverse goes from world to object. Yeah? And similarly for the direction, right? Why can I use the same M for both? Remember the directions, the homogeneous coordinate is 0, so you kind of ignore the translation. So it all kind of works out. Yeah, so at the end of the day, it's quite simple, right? If I apply M to this thing to go there, then I apply M inverse to get my array over here. And then I intersect my array with this guy, right? And then I can just use the same t value that I started with on the left, and I'm perfectly happy. Yeah? And this is a really sneaky trick. Notice that, like, if m scales things, then my direction can, like, crazy things will happen in the direction of my array. Like here, it rotated, it changed length, whatever. But that doesn't really matter. We're just operating in a weird warped view of the world. Yeah? One thing to notice is that, like, for example, let's say I just doubled the size of my sphere, right? Then, of course, what would happen to the length of the direction vector for my array? It would half, right? Notice that the inverse. Yeah? So what that means is that the direction vector, if it used to be unit length, is no longer unit length. So you have kind of two solutions to that problem, right? You can either normalize it or not. Yeah? So if you normalize it, then you just have to remember that when you go back, like when you go back to world coordinates, you need to unnormalize it. In other words, you need to scale your t value back to whatever that scale was that you used. Or if you're really slick, you just implement your ray tracer in such a way that it can handle non-unit direction vectors for your rays. Yeah? There's some other additional failure cases, right? You know, but I don't think it really matters actually. Let's keep through. Okay, so if I if I don't normalize my vector, then I don't have to deal with all these stupid boundary cases. I just have to be careful to have code that can deal with non-unit direction vectors, which is really what you should do anyway. Because otherwise, you're computing a bunch of square roots that you don't have to. Okay. Right. So remember that transforming points and directions are as simple as applying M or M inverse. But what do I need for rendering? I don't just need, like, did this ray like hit into the surface or not? Like, hooray, that's good. But I also need one additional thing, which is the normals of the surface, which we use for rendering. And so I apply M inverse to translate my array into object space, right? Including the direction and the source. What do I use? And now I compute the intersection of my object. I get a normal vector back. Then what do I do to get the normal vector in world coordinates? You guys remember? It's the inverse transpose of that, right? We covered that a few lectures ago. Yeah, and so the slides in here cover that as well. And that's just to make sure that the normals you get are something like at the bottom, rather than this thing on the top, which might kind of naively look nice because it looks like it has something to do with the circle, but they're not normals, right? Normals are perpendicular. And the nice thing is that this is like a totally recursive thing, right? Like I can apply 10 different transformations to my surface, and then what will happen is every time I intersect with the guy inside, you know, and then there's just some abstract subclass that intersects, and I don't care if there's more transformations sitting inside of there or not, it doesn't matter. Right? From my perspective, all I care about is did I intersect and was there? You can see that the ray tracing is quite elegant. Yeah, so we already covered this a few lectures ago, so we'll skip over it. The basic summary here is that the position is transformed by M, direction is transformed by M, then the normal is transformed by M, inverse transpose without a translation component. And I think we all kind of knew that, but it's worth thinking about carefully. Okay, so any questions about instancing and how we can shift and translate and rotate and scale objects in a ray tracing? Notice that if you combine this with CSG, you get really, really complex shapes that are just fusible. Yeah?
I was just about to ask about doing that with CSG because it seems like the array problem is harder in the sense that your arrays are in two different objects in object space. So
that's a great question. Yeah, so in CSG, remember that essentially the hack that we do for our ray tracer is just keeping track of our range of t values instead of the t word exercise. But here's the great thing. If I transform my ray and I don't normalize the direction vector, then when I untransform my ray, I go back to world space, that range of t values actually doesn't change. It's really sneaky, right? And because I applied the same transformation to my ray that I did to my object, right? And so in fact, although it might seem like it would be quite complicated because sort of like you're intersecting an ellipse with a sphere and there's a crazy shape, in reality this computation ends up being quite simple in practice. Yeah. It's really slick that you can do this. Yeah. Any other questions? All right, excellent. Okay guys, so that concludes our basic discussion of ray tracing, ray casting, and actually you're now equipped to render all kinds of pretty complicated shapes out of just a few simple primitives, right? And that's one of the really nice things about ray tracing. So when we continue next time, we'll talk about the ray tracing algorithm where you're allowed to spawn additional rays that go into your scene. And that's going to allow us to capture objects that reflect, refract, do the Pink Floyd logo with the rainbow, all that kind of good stuff. Okay, so I'm going to see you next Thursday, but you have class on Tuesday. There's a guest lecture by Ed, and it will not be filmed. So there. Okay, see you guys.